Hello, and welcome to this first lesson on the topic of alkenes. So this lesson covers largely sort of structure and physical properties and does a recap on various types of isomerism, as well as introducing a new type of isomerism, which is then expanded on in the second lesson. What it doesn't cover is stuff like cracking, because we'd really consider that, I suppose, part of the alkanes topic, but it is something you need to be familiar with, is, the production of alkenes. So then, let's kick off with the starter activity. So it's a pretty standard nomenclature starter activity. We've got 5 substances and I would like their UPAC names, okay? 4 of them are displayed formulae and one of them is given as a structural, which is a little more tricky. You might find it helpful to convert that to a displayed, but it's up to you how you handle that. You need to pause the video now and answer. Okay, so you should have some answers in front of you. Maybe you couldn't do everything, maybe you weren't sure, but you should have some answers in front of you. Okay, let's have a look. So we should have come up with a series of names like this: ethene, methylpropene, butanene, butene, and then 3,3-dimethylhexonene, which is one of the trickier ones, the one that was represented as a structural. Something else that's worth pointing out, it's always worth pointing out, is the comment on methylpropene. You don't need any numbers in this name. It's very easy to slip some superfluous numbers in. But remember, right, if you've got 3 carbons, this happens quite a lot, okay? So the structure's like this. There are 2 things we've got to factor. The first one is the methyl group, right? It has to be in the middle, because if it's anywhere else, then this is no longer propene, it's some kind of bute root. It's got 4 carbons in the main chain or the parent chain. So the methyl group does not need a number for that reason. Okay, it's the same logic as you get with methyl propane. The double bond also does not need a number because it can only go between carbons 1 and 2. No matter which way you twist or spin it and which direction you count from, it's the same position. Okay, so that's why we end up with no numbers. Always worth kind of just checking with that. All right. Very, very common one to be asked about. Methyl propane and methyl propene. Very, very common. Okay, so those are all alkenes, which is obviously relevant to the topic. Let's think about some basic kind of ideas to do with alkenes. So alkenes are often referred to as unsaturated hydrocarbons. That means that they contain at least one carbon-carbon double bond, as opposed to only containing single bonds between carbon atoms. They obviously contain hydrogen as well, and they follow a general formula just like alkanes do, although it's a different one. It's a simpler one, and it reads as CnH2n. So this is all kind of GCSE stuff. What you need to do is add this to your notes and then use the general formula to complete the molecular formulae of the 3 alkenes that I've asked for in the green boxes. So pause the video and do that now. Okay, so hopefully you're finding this straightforward because this is GCSE level stuff. Okay, the third one asks a little more for you, which is it asks you to realize that you've got 4 carbons in butanene. Okay, these molecular formulae don't tell you anything about the structure, they just tell you about the number of carbon atoms and the number of hydrogen atoms. All right, so it's probably worth pointing out that although it's butanene I've asked you about, the molecular formula for butene, which is a related molecule, would also be C4H8, because it doesn't tell you anything about the position of the double bond, the molecular formula. Good stuff. So I always kind of introduce functional group topics in organic chemistry with a little comment on boiling points, just to keep linking back to bonding and structure. So what we've got here is the 3 alkenes that we just did the molecular formulae for, now shown as a kind of mishmash between a displayed and a structural. Okay, and that's okay because, we've not been asked to draw them as structural. But the point I'm really trying to make here is that there'll be a gradation or difference in boiling points. And really, this is the same kind of thing as what happens with the alkanes. So you should be looking at this with your knowledge already and kind of sort of thinking about which molecule's the largest, which molecule's the smallest, what type of intermolecular forces we'll have. So hopefully what you've sort of realized is that ethene of these three will have the lowest boiling point, and butanene of these three will have the highest boiling point. That should come to you fairly naturally if you're at this stage in A-level chemistry, because you should know that these are non-polar molecules, and the strongest intermolecular force between molecules of ethene and between molecules of butanene, right, will be the van der Waals force. And the thing that governs the strength of the van der Waals force is essentially the size of molecules, the number of electrons, but we can think of it just in terms of size. Sometimes it's referred to as the molecular weight or the surface area, but the simplest way to think about it is largest molecule, highest boiling point, as long as there aren't other functional groups that change what type of intermolecular force we are thinking about. So if you're wondering about how to phrase this, here's your stock bonding and structure phrase, butanene, blah, 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 okay? This is the kind of thing that you should be very, very kind of confident with once you've studied A-level chemistry for a while, but it is easily neglected, which is why I always link back to it at the beginning of a topic. So you can take that in, copy it down, whatever you want to do. It's up to you, all right? It's not essential sort of knowledge for this topic. Then we're going to move on. So something which is kind of, you know, a small part of this is solubility. Again, I always reference this. Solubility is not a big deal in A-level chemistry for the most part. It is actually quite an interesting, complex component of chemistry, but the thing you need to just kind of strip it down to is the molecule polar? That's usually what you need to be thinking about. And generally, if the molecule's very non-polar, like alkenes are, it'll have poor solubility in water, all right? It's not quite the same as alkanes necessarily, but it's a similar sort of story because they still are hydrocarbons, okay? And that's as much as we're going to say about that. Okay. So some stuff that's kind of unique to alkenes is we sometimes look at the geometry of these molecules. So I've got a big displayed formula for ethene here, okay? So you should copy that down, right? Pause the video if you need to. And then we sometimes look at the shape and bond angles in hydrocarbons, and this can get a little bit confusing because it's not just a sort of totally straightforward shapes question, like when you've just got a single small molecule. Okay, ethene's probably as simple as it gets when it comes to alkenes shapes. So that's why we're going to start with it. So, right, let's think about this. When we're trying to sort of describe the shape in an alkene, what we're really thinking about is the shape with respect to a particular carbon atom. And in this case, it's going to be the same. Because ethene's a totally symmetrical molecule, the shape with respect to each of these carbons is going to be identical. And that's always going to be true either side of a double bond. Okay? So let's just look at one of them, take one of those bits of highlighting away. The easiest way to think about this is if I highlight that, and I highlight that, and I highlight that, okay? If I was teaching shapes, what I would say is, imagine that this molecule has 3 bonding pairs of electrons and 0 lone pairs, okay? Now, obviously, there's a complication here because ethene has a double bond. But when it comes to assigning the shape of a molecule, generally, a double bond, like the one we've got in this alkene, generally a double bond is treated as if it was a single bond, right? So you can imagine that section between the 2 carbons, imagine it's one bonding pair. It's not, but imagine it is for designating the shape. So then you think about what's in your memory or what you kind of reference by looking up, okay? 3 bonding pairs and 0 lone pairs, you should arrive at this kind of structure. This now might look a little familiar, okay? I've used X's and Y's to kind of describe it, right? But with respect to each carbon atom, right, we should arrive at the idea that the shape is trigonal planar, okay? So I've used the abbreviation WRT here. That's saying with respect to the carbon atoms either side of the double bond. We would say it's trigonal planar, okay? So remember, the name of that shape comes from the fact that it's flat, it's planar. Okay, and actually that's important for alkenes. And also it forms the interior shape of a triangle, right? If you kind of think about what the bonding pairs are doing. So we then also have to think about bond angle. And if you remembered trigonal planar, then you should also remember the associated bond angle. Okay, so you would probably have it as 120 degrees, right? Now, there's a slight complication here, which is that actually the angles between the bonding pairs aren't totally equal. This is probably to do with the fact that there's a double bond in that middle section. You don't have to learn these, although I am going to give them. What you actually get is 118 degrees between the CH bonding pairs and 121 degrees between the CHC bonding pairs. You don't need to know why that is, but again, it'll be to do with the double bond. You don't actually need to know those numbers. If you gave it as 120, then I'm sure the examiners would be absolutely fine with it because it's a good suggestion. So it'd probably be within that range of 118 to 121 degrees, if I had to guess. Okay. So there's a slight difference. Okay, we're going to note that. But in brackets, I've put 120 degrees just because, you know, that's the kind of value you're supposed to remember. Okay, there aren't any lone pairs that influence the shape, and so you shouldn't really, you know, be expected to make any adjustments to that value if you're thinking about ethene. It's uncommon to look at the geometry of ethene anyway, but it is part of the spec, you know, only a little bit, but it is. Okay, so if you need to, pause, rewind, make your notes as appropriate. I'm not kind of giving the instruction every single time here because these aren't tasks exactly. This is just instruction. One last little bit about the kind of, you know, peculiarities of alkenes. This is a fact that we won't come back to for ages, right? It's year 13 when we kind of revisit this. But actually, the length of the carbon-carbon double bond is also slightly different. So if you were to compare, for example, the distance between the two carbon atoms in ethane and the distance between the two carbon atoms in ethene, right, there would be a difference in length, the kind of measured distance, right? So carbon-carbon double bonds are shorter than carbon-carbon single bonds. This has a bit of an impact in a year 13 topic. Like I said, we're probably never going to talk about it again in this topic. Okay. So then, now we are into a task, right? So this is recap stuff from, you know, nomenclature and isomerism. What you need to do is draw the displayed formulae of the molecules in each pair. So for one, you draw butyne and butene. Look at them and compare their structures and name the relationship between them. So what type of isomerism is being exhibited by those two molecules? You do the same thing 3 times, okay? And each of them should exhibit a different type of isomerism. So pause the video and complete the task. Okay, so what we should have is a list of answers. Butyne and butene, position isomers. Butyne and methylpropene, chain isomers. Butyne and cyclobutane, functional group isomers. You could also have methyl cyclopropane as a functional group isomer, but that's not what I asked you for. So they are functional group isomers. Remember that cycloalkanes are a kind of very, very much a peripheral thing in A-level chemistry. The only time we really look at them, you know, is generally when we're saying they are functional group isomers of alkenes. They have this relationship with alkenes, okay, where they share the same molecular formula, all right, even though they don't have a double bond, which is why they are functional group isomers. Same molecular formula, different structural formula. So you should have just checked all your answers and see that you're happy with those before we move on to the next section. Okay. So it's time to introduce a new type of isomerism. It's worth probably pointing out that everything we looked at in that task was a type of structural isomerism. Okay, and there are 3 kind of subcategories within that. A completely different category of isomerism to structural isomerism is called stereoisomerism. So pause the video and write that stuff down, then we'll talk about it. Okay, so the first part of it is a definition that says the same structural formula, but the atoms are arranged differently in space. That can be a weird thing to get your head around. Sometimes it's described as a different spatial arrangement, which means the same thing, okay? Let's look at what that means as we go along. But the important thing is there are two branches, two subcategories of stereoisomerism that you need to know about for A-level chemistry. The first one is the one that we're going to look at in this topic, which is called sometimes geometric isomerism, or it's sometimes referred to as EZ isomerism. There is another kind of stereoisomerism called optical isomerism, but that won't be looked at until year 13. I'll literally just reference it here, just so that you know that there is another kind that we're going to look at later. So, what is geometric isomerism and how does it work? Let's have a look. So geometric isomerism needs sort of specific conditions to occur, okay? And there's a specific reason for it. Again, pause the video and make your notes as appropriate, then we'll look at what all these words mean. Okay, so to get geometric isomerism, you need to have kind of a mixture of atoms or functional groups in the alkene, right? And we'll look at a task about whether you get it or not sort of later on. An important phrase here is the bit that's in red, which is to do with rotation and how it can't occur, or it occurs much less, about a carbon-carbon double bond. So let's dig into that phrase. That's the kind of first bit we're going to do. So this is not an alkene, it's an alkane, ethane. All right, and something that you might not be aware of, because unless you've played with model kits or looked at three-dimensional structures, it's very difficult to kind of, to see this. But something you might not be aware of is that in alkanes, you get rotation within the molecule. So what we mean by that is, if I, for example, label this, well, these three hydrogens with numbers, they don't mean anything, they're just labels 1, 2, and 3, okay? If I say that hydrogen 1, that hydrogen specifically, is in that position, you might have realized that when you're doing your nomenclature and isomerism stuff early on in year 12, a lot of the time, it doesn't really matter if you point your hydrogen up or down. It doesn't matter if you point your bromine up or down. A lot of the time, it doesn't matter, okay? And that's true whenever you don't have carbon-carbon double bonds. So what we're getting at is that actually you get this kind of spinning, right? And it's basically saying this whole section, this is going to look messy, but this whole section can kind of spin round, right? And those hydrogens might actually swing round and occupy a different position. And actually, there's a whole kind of sub-branch of chemistry that you do in undergraduate level that kind of explores this in more detail. What I'm trying to get at is, let's say, for sake of argument, you're looking at this molecule of ethane specifically. Over time, what you might see, it might be a very short time frame, what you might see is that if you've labeled those hydrogens, and again, this is all kind of weird hypothetical explanation, but if you've labeled those hydrogens, it might be that they've moved and changed position. And that's because you get this constant rotation. And obviously that can happen on the other side too, right? So the point about this is that it doesn't actually matter how you draw your displayed formula if there are no double bonds in your molecule in terms of which position each thing occupies, right? So a lot of the time when you've been drawing molecules with different functional groups, like I keep saying, you've probably seen things like, I don't know, let's say it's 2-chloropropane for the sake of argument. So obviously this isn't ethane, this is 2-chloropropane. The point I'm trying to make is, I've put my chlorine here, okay? That's fine, but it would also be fine if the chlorine was here and the hydrogen was in the position where the chlorine is, because actually in reality there's rotation, right? So it might be that they're moving position. Obviously I can't start putting my chlorine over here because then it wouldn't be 2-chloropropane, it'd be 1-chloropropane. But with respect to how everything's attached to a single carbon atom, there's a flexibility there. So that's something we don't really discuss, even though, you kind of get taught, well, it doesn't really matter which way you put this atom or that atom at the beginning. The point that we're trying to make now is that actually, right, in an alkene, any substance that has a carbon-carbon double bond, it actually does matter where you've put things, right? There is actually a difference. And the reason for that is this idea of rotation, right, is restricted, okay? You do not get this flipping around of the hydrogens or whatever it is that's attached to the carbons. And that's because the double bond, it basically presents itself as a barrier, right? There's a more complex explanation for pretty much everything we study in A-level chemistry, but think of it as, it's in the way, okay? The phrase that you have to know is restricted rotation about a carbon-carbon double bond. And what we're saying is, if we've said that this hydrogen is in position 1, that's where it stays, right? This one in position 2, that's where it stays. You don't get this flip-flopping like you do in ethane, okay? So I've made a mess of all of this stuff, and I don't think that it's really relevant for you to copy down. It's really just part of how my explanation works, all right? We're going to use, some specific molecules to try and explain this. So here's a sort of, mini task for you. If we think about the fluoroalkene, or the haloalkene, 1,2-difluoroethene, my task is draw the displayed formula of this molecule. All right, and don't worry what you come up with, but just try and draw it. Pause the video and have a go. Okay, so here's my question. Did you draw this? Or did you draw this? Worth pointing out that if you drew something with the fluorines on the bottom, and the hydrogens on the top, like I've done underneath it, that's the same as the thing that's above it, right? Don't worry about that. So that's the same logic. Again, if you had the fluorines bottom left and top right instead of top left and bottom right, that would be the same as the structure that's on the right. I'm not going to draw that, but that's what I'm getting at. So did you draw, which one did you draw, right? The point is that it could be either, and the designation for which one it is has a specific name. And this is actually an example of geometric isomerism, because the direction that the various atoms are pointing with respect to the double bond, right, actually makes them different. They have a different arrangement in space, okay? However, their structural formulae would be identical. So let's think about that. We've got CHF, CHF, we've got CHF, CHF, right? The structural formula doesn't actually tell you which direction the fluorine atoms are pointing in, okay? And that's what makes these geometric isomers. They have the same structural formula, but they have a different arrangement of atoms in space. Right then, let's look at them properly. So the designation for these takes the form of a capital letter that goes at the beginning of the UPAC name, okay? And it usually gets put in brackets. You designate these things either as the E isomer, as we've got on the left, or the Z isomer, as we've got on the right. Okay? So, an E isomer is called as such because the E stands for the German word entgegen, which means opposite, okay? Z stands for zusammen, which means together. So what do we mean by opposite and together? Well, really, we're talking about the fluorine atoms, okay? You could also reference the hydrogen atoms, but for reasons we'll get into in next lesson, it's the fluorine really that's causing this designation, right? What we're getting at is, if you sort of trace a line, you don't have to highlight this, but that's what I'm doing to explain it. If you sort of trace a line from one fluorine to another across the double bond, you find that these atoms are pointing in opposite directions. right? They're pointing in opposite directions away from each other across the double bond. By contrast, if you do the same thing for the Z isomer, they are pointing in the same direction, or they're pointing together away from the double bond that way. So remember, right, the only reason that this can happen in alkenes is because of that restricted rotation. If the fluorine atoms end up in those positions, that's where they stay, okay? And that's why there is this additional kind of way of labeling or naming these molecules, E or Z. So we've introduced it, we've looked at the German terms. We're going to further complicate this next lesson, but for now, let's focus on something kind of more fundamental, which is in this molecule, this can happen. Geometric isomerism can occur. And the reason for that is it kind of follows this rule that we talked about earlier. So if we just track back upwards, there are two different functional groups at each side of the double bond in this molecule, right? In other words, the fluorine atoms are on opposite sides of the double bonds. Let's think about this molecule, which is a position isomer of what we were just looking at. There is only one form of 1,1-difluoroethene. This substance does not exhibit geometric isomerism. There are no geometric isomers. There is no E form or Z form. And the reason for that is, even though it's got exactly the same molecular formula, right? It's got the same number of carbons, fluorines, and hydrogens. The fluorines are both attached to the same carbon in this molecule, okay? Which means that there is no kind of relative positioning of them on opposite sides of the double bond. They're both kind of pointing away from that carbon on the same side of the double bond. So the reason that we're looking at this, right, is to try and kind of, hammer home the idea that not every single alkene exhibits geometric isomerism, okay? In this case, because of where the fluorine atoms are, sorry, I could see the video, just needed to catch up with me there. Because of where the fluorine atoms are, right, there is no geometric isomerism, okay? Same for in ethene as well, right? We didn't really discuss this, but just plain old ethene, it's all hydrogen, so there's no geometric isomers. This can get a little confusing, but we're going to do a task to hopefully consolidate and understand a little bit, okay? So this is the last section of this lesson. What we have is a list of UPAC names. All you need to do is draw the molecule, right, in whatever way you want. It doesn't have to be a displayed formula. It could be sort of condensed a little bit. Draw the molecule and try and guess. It's almost guesswork at this stage. Try and determine if you think it can exhibit geometric isomerism. So you do not need to try and draw the geometric isomers. You just need to tell me, is it yes or no? Can you get geometric isomerism or not? If you're not sure how to proceed, just think back to the examples that we just did. You're thinking about what's on either side of the double bond. Pause the video and attempt these 5 questions. Okay, so you should have a list of answers. You might not have been totally sure, but let's have a go. Here is pent-2-ene, okay? So in this molecule, right, what you have is something that can form geometric isomers. And it can, really, because the alkyl groups, the methyl group and the ethyl group, right, on either side of the double bond can point in different directions. Now, as it happens, I've drawn the Z isomer. I didn't ask you to designate that, but that's what I've drawn. They're on because they're on the same side, they're together, okay? But the point is it can, right? We could have a different orientation for the alkyl groups. In this molecule, it's not possible. And the reason it's not possible is to do with the fact that there's 2 hydrogens attached to that carbon. They're the same, right? They're the same kind of atom. So there is no designation. There is no way of kind of tracing a line, along the double bond, okay? For hex 3ene, similar sort of story to the first example. The answer is yes. Okay. You've got alkyl groups again, slightly different to last time, but this form is also the Z isomer. There's no reason for that. Like I said, you didn't have to work out which it was, but you can get geometric isomers here. A complex example, right? This one. There are lots of methyl groups in this molecule, but it's that same kind of idea where actually, well, I can't say one of these is E or one of them is Z. There is no difference, you know, because all of the groups that are attached to the carbon atoms either side of the double bond are completely the same. Okay, so no geometric isomers here. Exactly the same logic for number 5. We've got 4 fluorine atoms. No geometric isomerism. So hopefully you're happy enough with that. It is sort of tricky, but you do get a sense of how it works. And when we introduce some more complex rules next time, you'll start to sort of build confidence a little bit. Okay, that's this lesson done.